All right. Hello and welcome to another lesson or another class on our chemistry jam syllabus, and we've treated quite a number of topics so far. Adventure, you've not been um, following before now. Please get the video and make sure that you watch all the classes all the topics rather that have been treated so far in the chemistry jam syllabus. So today we're going to be looking at a new topic, and the topic is titled Kinetic Theory of Matter and Gas Law. Kinetic Theory of Matter and Gas Law. My name once again is Anjori Oluwafemi Excel, and I will be your teacher in this class. And for this particular topic, um, without further delay, let's look at our learning objective for this particular topic. Okay, our learning objective are the following. By the end of this lesson, students should be able to explain the kinetic theory of matter and its application to the different states of matter. It is also expected that by the end of this lesson that students should be able to describe phenomena supporting the kinetic theory, including melting, vaporization, boiling, freezing, and condensation in terms of molecular motion and then Brownian movement. It is also expected that by the end of this class that students should be able to state and apply Boyle's law, Charles' law, Graham's law, Dalton law of partial pressure, and it's also expected that we should be able to derive and use the combined gas law and the ideal gas equation, which is the PV equals to nRT. So it is also expected that by the end of this lesson, I should be able to understand the relationship between, or state the relationship between vapor density of gases and their relative molecular mass. So states the relationship between vapor density and their relative molecular mass. Okay. Now let's start off with the introduction for this topic, and let's establish a little about the two things that we're going to be considering, which is the kinetic theory of matter and then gas laws. We said that kinetic theory of matter posits that all matter comprises particles in constant motion. Now, the theory explains the different states of matter, that is the solid state, the liquid state, and then the gaseous or the gas state. Okay. Now, based on particle movement and then energy levels. So that's what the kinetic theory of matter, it all is all about, and that's what we're going to be looking at as we move into the body of the topic as we move as we go deeper into this topic that we are considering. Gas laws describe the behavior of gases in relation to pressure, volume, and temperature. The key laws we shall be covering in the course of this lesson include Boyle's law, Charles' law, ideal gas law, Graham's law, and Dalton's law of partial pressure, combined gas law, and we're going to be looking at molar volume, then atomicity of gases. Okay, all right. So we are going to be looking at all that as we go, as we move along in this lesson. Okay, all right. Having said that, let's look at the first slide. That's the state of matter. This is fundamental. If I ask you what are the three states of matter, you can easily tell me or give me what they are. So we want to start from the known, what we know already, then we'll push it forward, and then we'll now move deeper into the topic proper. So The three states of matter includes solid, liquid, and gaseous states, and they can be distinguished by the motion of particles they are made up of and the attractive force between their particles. So what I did is just to create a table to look at the three states of matter, their properties, and then some differences, just doing a contrast between the three states of matter. So when we have the solid, one of the things you notice about the solid state of matter is that it has a definite shape and volume. It has a definite shape and volume. The liquid state, on the other hand, have no definite shape and it does not have a definite volume also. Okay. The gaseous states, on the other hand, have no definite shape and volume. So in terms of shape and volume, we can actually compare the three states of matter that we have. Okay. Now, in terms of density, solid is very dense, liquid is less dense, and then gases are the least dense among the three states of matter. So, in terms of ability to compress them, solid are incompressible. It is very, very difficult to compress a solid. Liquid are also incompressible. Okay, gases can easily be compressed, and that's why you can put them into a gas cylinder. You can put them into any container. You just compress it, and then it fits in perfectly, and and that's that for gases. They are compressible. All you just need to do is just exert pressure, and then you're able to compress gases. Okay. Now, in terms of mass, solid have fixed mass. Liquid to have fixed mass, and then gases also have fixed mass. Okay. Um, in terms of their particle vibrating or rotating about a fixed point, we said particles for solid, they have the ability to vibrate and rotate about a fixed point, and particles for liquids vibrate and move about within a restricted space. Then for gases, particles move about constantly at great speed and at random, to see it's constantly moving and it's moving at random, it's much more freer. The particles in gases are much more free to move around. Yeah, so that's that for that. So we have made a comparison between the three states of matter. We've established what the three states of matter are. Okay. And let's move on to the next one. Look at the changes of states. There are different change of states that we notice. We change of states is basically a transition from one state of matter to the another state of matter. So when you have a transition that includes solid um, moving down to become liquid, solid moving down to become liquid, we call that particular phenomenon or change of state to be melting. And then when you have liquid, moving to become a solid, that change of state is what we call freezing. And in a situation whereby you have our solid moving to become a gas, that's more like sublimation. And then when you have a situation whereby liquid now turns to gas, like what we see when we boil water, that is evaporation. And then when you have gas, transforming in state to become liquid, that is condensation. Okay. All right. So these are the various changes of states that we have. And I'm going to be touching on some of them and try to explain them from the kinetic theory standpoint. Okay. All right. Now, what are phenomena now supporting the kinetic theory of matter? What are phenomena that supports the kinetic theory of matter? Now, melting is one of the or phenomena rather. So this is a process where a solid turns into a liquid when heated. That is what melting is all about. A solid will turn into a liquid when heat is applied or when it gains heat. Now, when a solid is heated, the particles acquire greater kinetic energy and move violently. So what happens is that when you supply heat to a solid, the particles that make up the solid will, they will acquire greater kinetic energy. They were fixed before, they could not move so well before, but they will acquire greater kinetic energy and begin to move violently. No. Now, a point is reached when the forces of vibration overcomes the cohesive forces holding the solid particles together, and the crystalline structure collapses. Now, the particles are no longer held in fixed position, but are free to move about, and the liquid state is reached. The temperature at which this occurs is called the melting point of the solid. So that's one of the phenomena that supports kinetic theory. It is supplied or added to the solid. It acquires greater kinetic particles in the solid acquires greater kinetic energy, and then they move more violently. That is, the particles move more violently, and it will get to a point that the solid will become a liquid, and this point is what we call the melting point of the solid. So, what happens basically with melting is that energy increases, and then you have a state whereby the solid now transforms into a liquid, so to speak. So that's that for that. Now, vaporization is another phenomenon that supports the kinetic theory of matter. And vaporization can be defined as the process in which the liquid state changes into the vapor state as a result of an increase in temperature. The kinetic energy of the molecules increases. Due to the increase in kinetic energy, the force of attraction between the molecules reduces. As a result, they escape into the surrounding in the form of vapor. This process involves the consumption of heat energy. So, vaporization is another phenomenon that supports the kinetic theory of matter, and basically, it is a translation or a transformation in which the liquid state of matter changes into vapor, the gaseous state, as the case may be. And the reason is because there's an increase in the temperature, the kinetic energy of the molecule increases, and then this increase in kinetic energy is basically due to the force of attraction between the molecule reducing. So the force of attraction between the molecule reduces, so you discover that the molecules now have the freedom to move very, very fast when the temperature is increased. So as a result, they escape into the surroundings in the form of vapor, and what happens basically is that energy is consumed, by the liquid, and then it increases the kinetic energy. It lets the movement of the particle to become more freer until it gets to a place of being a gas, and then it escapes into the surrounding. Okay, all right now. So we have different types of vaporization. One of the type of vaporization that we have, or vaporization can be divided into two types. One, evaporation, and then boiling. Evaporation and boiling. These are the two types of vaporization that we have. Now, evaporation can generally be defined as a process by which a liquid is transformed into vapor. A process by which a liquid is transformed into vapor. And most of us have the experience of witness evaporation taking place before. Is either you were the one that initiated it, or somebody did while you were there. A very good example is when you boil water, evaporation will occur. You set the water at the room temperature, you set it on your gas cooker or your hot plate or whatsoever that can supply heat. Now, when the heat is supplied on the kettle or the pot, what happens is that the particles or the molecules of the liquid now start, moving so fast, and it will get to a point that they now transform into vapor, and they escape into the atmosphere or the environment. So that's basically what it is. So boiling is the rapid vaporization of a liquid, which occurs when a liquid is heated to its boiling point. A liquid boils at a temperature at which its vapor pressure is equal to the pressure of the gas above it. Okay, so basically that is what it is. These are the two types of vaporization we have, but there's a difference between boiling points and evaporation. And you can actually see the diagram. And from the diagram, you'll notice that one is actually a surface phenomenon, and the other one is holistic. It is occurring virtually everywhere in the vessel that that phenomenon is taking place. So evaporation differs from boiling because evaporation is a surface phenomenon, unlike boiling, which is a bulk phenomenon. So you have a complete or a total, experience with boiling, but with evaporation, it's actually a surface experience or a surface phenomenon. It takes place at the surface of the vessel. So boiling will come up when the particular liquid hits its boiling point, and then you see it happening virtually everywhere in the vessel that you are eating or that you have set on fire to boil, so to speak. While evaporation, it's a surface phenomenon, occurs at the surface. It is not something that happens all over the vessel, but at the surface, and that's basically the difference between evaporation and boiling. Okay, so the next phenomenon that supports kinetic theory of matter is freezing. And we said freezing is the process that causes a substance to change from a liquid to a solid. It causes a substance to change from a liquid and to a solid. Now, freezing occurs when the molecules of the liquid slow down enough that the attraction causes them to arrange themselves into fixed position as a solid. Now, according to the kinetic theory of matter, freezing happens when the particles in the liquid lose enough kinetic energy due to cooling, causing them to slow down significantly and become tightly packed together, forming a structured solid, where the attractive force between particles are strong enough to hold them in fixed positions. Essentially, the molecules lock into place, resulting in a solid state with a definite shape and volume. So that's basically it. And what happens with freezing is that the liquid loses enough energy. Energy is lost. Unlike for vaporization, whereby its energy increases, the particle increases in energy, and then it gives us the vapor or gases into the environment, as the case with. But for freezing, there's a loss of energy. Kinetic energy is lost, and then cooling takes place, and then the liquid aggregates themselves, and the force of attraction between them becomes stronger. Then they transform into a solid, and excuse me, excuse me, please. Like I was saying, it transforms into a solid, and then they have a close or a very strong force of attraction between the particles. So that's what takes place with freezing. Okay. The next phenomenon that supports kinetic theory of matter is condensation. Now, the kinetic theory explains condensation as the process where gas particles lose energy and becomes liquid. So gas particles lose energy and they become liquid. According to the kinetic theory of matter, particles in a gas have the highest amount of kinetic energy. We have said this before, we've established this before. So gases basically have the ability to move freely and rapidly in all directions as versatile movement. They just move, they are very loose, they move about. However, when this gas particle lose energy, often due to a decrease in temperature, they start to slow down and come closer together. This process is known as what? Condensation. That is what we call condensation. They lose energy, and then basically because of reduction in temperature, energy is lost, and then the particles slow down, they come closer together, and we can now have those gases, being converted into liquid in that process. A very good example is what we see in our glass cup with cold water. When the warm air or warm moisture comes on it, what happens is I start seeing water around the back of the container or the cup that you have put the what's it called, the ice block water or the cold water, as the case may be. And this is a very good example of condensation, Okay, all right. So we've explained that. Another thing again that we need to touch on is the Brownian motion. Brownian motion was first observed by the botanist called Robert Brown in 1827. And it refers to the random zigzag movements of particles suspended in a liquid. Now, this phenomenon results from collision between the suspended particles and the much smaller, rapidly moving molecules of the fluid. Okay. Now, the kinetic energy of these fluid molecules causes them to strike the suspended particles unevenly, leading to their erratic movement. Okay. In the context of condensation, Brownian motion plays a significant role. And this is because condensation is a process by which a gas transforms into a liquid when cooled. As the gas cools, its molecules lose kinetic energy and move closer together, allowing what we call intermolecular forces to pull them into a liquid state. Now, Brownian motion facilitates this process by enabling gas molecules to collide and coalesce into liquid droplets. The random movement increases the likelihood of molecular interaction necessary for the phase transition from gas to liquid. Okay, all right. So that's that for Brownian motion in relation with kinetic theory of matter and then condensation. Okay, all right. Having said that, let's move into the laws now, the gas laws. But before I go into the gas law, please don't forget all that we have talked about in the course of explaining kinetic theory of matter. We started off with the state of matter, and then we did a comparison between the state of matter that we have, and then after that, we looked at the changes of states. I tried to explain them, and then we now took them one after the other, as phenomena that support kinetic theory of matter. So we looked at melting, we looked at vaporization, and we said vaporization can be divided into evaporation and then boiling. We made a contrast between what boiling is and what evaporation is all about. We also touched on freezing and explained what freezing is all about. And then in relation with the kinetic theory of matter. Okay, let's jump into gas laws now. Gas laws. Yes, and the first one we are looking at is Charles' law. Now, a French chemist named Jacques Charles found the relationship between volume and temperature under constant pressure. And what does Charles' law state? Charles' law states that the volume of a given mass of gas is directly proportional to its absolute temperature or temperature in Kelvin, provided pressure remains constant. Now, it states that the volume of a given mass of gas is directly proportional to its absolute temperature or temperature in Kelvin, provided pressure remains constant. So the participating entities here are the volume, and then what's it called? And then the temperature. Those are the participating. Those are the participating entities here. So a very good example is a container of a confined gas is heated. Its molecule increases in kinetic energy and push the movable piston up outward. resulting in an increase in what? In volume. Temperature increases, volume increases. So it's actually a direct relationship between these two. Okay. Now, mathematically, volume is directly proportional to temperature when P is at constant. That's the mathematical representation for Charles' law. So, V will be equals to what now? Will be equals to KT, where K is a constant, or K can be V, that's the volume divided by the temperature. So here, our V is our volume, T is temperature, and then K is the mathematical constant. Now, for two gases, 1 and 2, V1, T1 equals to K, and then V2, T2 equals to K, which is a constant, okay? Therefore, our V1 over T1 can be equated to become to V2 over T2, and this is the gas at the Charles law. V1 over T1 equals V2 over T2. So when you see questions like this in JAM and you've seen all the parameters and what you are looking at, maybe you're asked to look for the volume, the final volume, whereas we're given the initial volume and then the initial temperature and final temperature. So what you need to do is to remember this formula V1 over T1 equals to V2 over T2, plug it in, and then you will get the right answer. Okay, so we try to describe interpreting of the terms. You know, V1 is initial volume, T1 is initial temperature, V2 is final volume, and then our T2 is final temperature. Graphically, this is how we represent the Charles law. So this is a graphical representation of Charles law. Like you can see it for Celsius scale and also for Kelvin scale. This is the representation for graphical representation for gas law. So please let's take note of it. You know, V is directly proportional to T. So as V increases, as T increases or temperature increases, volume will also increase accordingly. Okay, our kinetic theory explains Charles' law. An increase in temperature increases increases the average kinetic energy, and the molecular gas move more rapidly and collide with the walls of the container. So at constant pressure, the volume of the container increases with an increase in temperature. Conversely, a decrease in temperature lowers the average kinetic energy of the gas molecule and also lowers the frequency of collision of gas molecule. So this is how kinetic theory explains Charles' law. Okay. All right. So the next thing that we want to look at is an example that we can use to we can deploy the formula into and then get what's it called? Get the answer or the unknown as the case may be. Okay. Okay. So just a moment. Coming. I want to click do something. Okay. So pardon me. Let me quickly go back to the slide that I stopped at. And then we'll pick it up again from there. Just a moment. I'm coming. So So we're looking at calculations involving Charles' law now. That was what we were looking at. Um, let me quickly stop this one from showing here, and then we continue from there. Okay. So there's a question. It said the volume of a given mass of gas at 30 degrees Celsius is 600 centimeters cubed. If the pressure remains constant, determine the temperature when the volume is 800 cm cube. Okay. Now, according to Charles' law, V1 over T1 equals to V2 over T2. So we've established that from Charles' law. If you look at this question closely, there are some parameters that we have been given, and they are known parameters. Like take for instance, the initial volume was given to be 600 centimeters cube. The initial temperature was given to be 30 degrees Celsius. And please don't forget that if it is given in degrees Celsius, you need to convert it to Kelvin. And how do you do that? Whatsoever it is that was given to you in Celsius, you simply had 273. So once you had 273 to it, it will convert it to Kelvin, which is what we use or what we'll be using in our calculations and in this calculation and in subsequent ones that we're going to be looking at together. So our final volume was also given to us to be 800 cm cube. So the only thing that is unknown here is the final temperature, the final temperature. And if you look at it closely, we can make our T2, which is the final temperature, the subject of the formula. And that will be T1 V2 over V1. If you put in the values and then you punch your calculator, you will end up having 404 Kelvin, or if you so desire, 131 degrees Celsius if you want to convert it to degrees Celsius. So this is a simple application of the equation, or sorry, the formula for calculating Charles' law. Okay, all right. So let's move on to the next one now, and we'll consider the Boyle's law or Boyle's law. An English physicist, Robert Boyle, in 1662 studied the effect of pressure change on gas volume. His observation led to what we call the Boyle's law. And what does it state? Boyle's law states that the volume of a fixed mass of gas is inversely proportional to its pressure, provided temperature remains constant. And these formulas are very, these laws are very important that you should be able to state them, accurately. So the volume of a fixed mass of gas is inversely proportional to its pressure, provided temperature is or temperature remains constant. So it means that at constant temperature, an increase in the pressure exerted on a fixed mass of gas leads to a decrease in the gas volume, and vice versa, as the case may be. So it's an inverse relationship. That's just basically what it is. Okay. All right. Now let's look at the mathematical representation of Boyle's law. Now, how do we represent Boyle's law? Mathematically. So basically, we say V is inversely proportional to the pressure. Okay. So this proportionality can be converted into an equation by adding what we call a constant, which is K. So V now will be equals to 1 over P, then multiplied by K. So our V will now be equals to K over P, or PV equals to K. I think we understand to this point. We should, okay? Still basic, okay? So where V is the volume, P is the pressure. Now, when we use the expression PV equals to K, for gas 1, we have what we call P1 V1 equals to K. Now for gas 2, we have P2 V2 equals to K. Now since K equals to K, then P1 V1 equals to P2 V2 at constant temperature. This is the formula for Boyle's law. So our P1 is our initial pressure, P2 is the final pressure, our V1 is the initial volume, and then V2 is the final volume. Okay, having said that, let's look at let's consider, before we look at the example, I said Boyle's law can also be restated as the pressure of a given mass of gas being inversely proportional to its volume, temperature remaining constant. Okay. But let's look at the graphical representation of Boyle's law. You can see what happens, as pressure increases, volume will decrease. It's an inverse relationship. And so that is P against V, and then P against IV. And in C, we have a graph of PV against P, or V as the case may be. So this is the graphical representation for Boyle's law. Okay. All right. Now, how does kinetic theory, or how does kinetic theory explain Boyle's law? At constant temperature, if the pressure of a given amount of gas is doubled, its volume will decrease by one half. Conversely, if the pressure is decreased by one half, the volume will double, and that is what happens, when the temperature is constant. And this is one of the explanations that the kinetic theory uses in explaining Boy's law. Okay, let's look at this question. A given mass of a gas occupies a volume of 300 cm cube at 900 millimeter mercury pressure. Calculate the volume occupied by the same gas at 750 millimeter mercury if the temperature remains constant, So when we solve this one, we bring in the Boy's law, which is the P1 V1 equals to P2 V2, okay? And we have been given certain values, like the initial pressure was given to us as 900 mm Hg, that's millimeter mercury, and then the initial volume was also given to us. The final pressure was given, but we were not given the final volume. So we are calculating, we are looking for the final volume V2. So what we'll do is that we'll make V2 to become the subject of the formula in the Boy's law equation, and Boy's law um, the Boy's law equation, so to speak. So when we make V2, the subject of the formula is now P1 V1 over P2. You plug in the value and then you end up having 360 cm cube as the final volume. Okay. Okay. Now the next thing we need to look at is the general gas law. From Boy's law, we know that P1 V1 equals to P2 V2, and then we equally know that from Charles' law that V1 over T1 equals to V2 over T2. Now, for when we keep the temperature constant and replacing V2 with Vx, we now end up having what P1 V1 equals to P2 V2. So our Vx will now be equals to P1 V1 over P2. Now, that's from Boy's law. From Charles' law, on the other hand, now keeping the pressure constant and replacing V1 with Vx, what we end up having will be our V1 over T1 equals to V2 over T2, and then, like I said, replacing V1 with Vx, so we have Vx over T1, which will be equals to V2 over T2. Then our Vx equals to P1 V1 over P2. Then our Vx, from the other one, we establish it that our Vx will now be V2 over T1 over T2, okay? So I haven't done that. The next thing that we need to do is to combine equation 3 and 4 together, where we generated our Vx. The first Vx from Boy's law is, and how did we generate the Vx? We replace our final volume with Vx. So from the two equations, we're able to generate these values. Then we combine. When we combine them, it means that our P1 V1 over P2 will be equal to V2 T1 over T2. So when we cross multiply, we'll end up having P1 V1 T2, which equals to P2 V2 T2. Now, dividing both sides by T1 and T2, will give us the general gas law. And what is the general gas law? P1 V1 over T1 equals to P2 V2 over T2. So that's our general gas equation. So we are just combining from Charles' law and Boy's law, and then we end up having our P1 V1 over T1, which equals to P2 V2 over T2. Okay, all right. See, so that's that for that. Then another thing that we need to look at is this question. It says an ideal gas at 30 degrees Celsius and 1.01 times 10 to the power 5 Newton per meter square occupies a volume of 200 cm cubes. Calculate the volume at STP, that is standard temperature and pressure. Now, according to general gas equation, P1 V1 over T1 equals to P2 V2 over T2, where our P1 equals to 1.01 times 10 raised to the power 5 Newton per meter square. And then our V1 was given, our T1 was given, and then our P2 was standard pressure. And standard pressure is because basically 1.01 times 10 to the power 5 Newton per meter squared. Then our V2, our V2 we don't know. Then our T2 is the standard temperature. And the standard temperature in this regard is at 273 Kelvin. Now, when we plug in those values, I will make V2 the subject of the formula. What we end up having is a volume, a final volume of 180 point 20. So when you use your calculator, you can actually get this value out. Okay, all right. So start with that. Ideal gas equation. The ideal gas equation is a combination of Boyle's law, Charles' law, and and Avogadro's law. So basically, our ideal gas equation states that PV equals to nRT, where our P is the pressure, V is the volume, N is the number of moles, and then R and then R is the molar gas constant, T is the temperature in Kelvin, and then R can be 8.31 joule per Kelvin per mole, or 0.082 atmosphere TMQ per Kelvin per mole, as the case may be. So that's the ideal gas equation. The next thing is to know that our ideal gas equation equals to our integral equation equals to PV equals to what? nRT, and then N is the number of moles, and the number of moles basically can be calculated using mass over molar mass. That's how we calculate the number of moles, and basically, what happens is that we can have a substitution of N in the ideal gas equation with M over M, that is, with the number of moles and then the molar mass, as the case may be. So when we substitute, our ideal gas equation will be looking like PV equals to M, small letter M over capital letter M, RC. Don't forget our small letter M is the mass, and then the capital letter M is our molar mass. Okay. All right. So let's look at this question to test out the equation that we just generated. Calculate the volume occupied by 2.5 moles of an ideal gas at minus 23 degrees Celsius and 4.0 atmosphere. Our R is given to us to be 0.082. Okay. So basically, our PV equals to nRT, and then we said our pressure is 4 atmosphere. Now our volume, we don't know what it is. Our R is 0.082, and then our temperature, like I said earlier, we convert it to Kelvin by adding it to 273, and then we have 250 Kelvin. Our PV equals to nRT. So making V the subject of the formula will become nRT over P. Then so our V is nRT over 4, which is the 4 atmospheres. So when you plug in the values, you end up having 12.8 dm cube, 12.8 dm cube. So please, I want to quickly take a pause again and try to reflect on some of the things that we have touched on. We have looked at Boyle's law, we have looked at Charles' law, we have looked at the general gas equation, and then the ideal gas equation. And we have tried for all these gas laws to ensure that we bring a working example that we can all relate with. So it is very, very important. So let's let's quickly pause again for you to reflect on what you have thought so far. And if you have questions, please, if you have questions, so kindly put those questions in the comment section so that I can be able to pick them up and then respond to them as accurately as I can. So another thing that we need to also look at is the Dalton's Dalton's law of partial pressure. Dalton's law of partial pressure, and basically John Dalton in his experiment and study of gases observed that each gas in the mixture exerted its own pressure on the walls of the container as if no other gas was present in the container. Now, in 1801, his observation was put forward as Dalton's law of partial pressure, which states that in a mixture of gases that do not react chemically together, the total pressure exerted by the mixture is equal to the sum of the partial pressures of the individual gases present in the mixture. Okay, so that's the Dalton's law of partial pressure, Dalton's law of partial pressure. Okay. Having said that, let's take the notch further and try to bring the mathematical representation. So this implies that if gases A, B, and C and up to like maybe infinity or n are in a gas or are in a vessel rather, the total pressure PT exerted on the walls of the vessel can be determined as what? PA plus PB plus PC, which will be equals to, up to like PN, so to speak, where PA, PB, PCs, and PN are the partial pressures of individual gases A, B, C, and N, respectively. Okay, let's look at this particular question to explain that equation or that law. 200 cm cube of nitrogen gas at a pressure of 500 millimeter mercury and 100 cm cube of carbon dioxide at a pressure of 50 millimeter mercury were introduced into a 150 cm vessel. What is the total pressure in the vessel? Now, the first thing that we need to look at is that the volume of nitrogen is 200 cm cube. The pressure exerted by nitrogen gas is 500 millimeter mercury, and also for CO2, the volume is 100 cm cube, and then the pressure exerted is about 50 millimeter mercury. So we also know that the volume of the vessel is 150 cm cube as given to us in the what's it called in the question. Okay, now the next thing is we look at it, volume of the gas is over the volume of the vessel multiplied by the pressure of the gas. When we do that, we'll end up having our pressure for nitrogen to be like 666.67 millimeter mercury, and that for all CO2 will be 33.33 millimeter mercury. So according to Dalton's law of partial pressure, P total or the total pressure is P equals to PA plus PP plus PC up to PN, where our P total in this case will be equals to the pressure for nitrogen and then the pressure of CO2. And we have calculated that to be 666.67 for nitrogen and then 33.33 millimeter mercury for CO2. So when you add them up together, you end up having a total pressure of 700 millimeter mercury. So that is basically what partial pressure is all about. Okay, so we've established that, and then we can move on to the next now. So the next thing that we need to look at is the Graham's law of diffusion. Graham's law of diffusion. Okay, Graham's law of diffusion. Okay, in 1833, Thomas Graham, an English chemist, performed an experiment and discovered that a lighter gas diffuses through a medium much faster than a heavier gas. So he carried out further experiments to investigate the relationship between the rate of diffusion of the gas and its density. And his findings led to Graham's law of diffusion, which states that at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density or relative molecular mass. So please, let's take note of that. Graham's law of diffusion states that at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density or relative molecular mass. Okay, so that's Graham's law of diffusion. So let's look at the mathematical representation of this law now. The rate of diffusion is inversely proportional to the density. That's one, the square root of the density now. So what we have is rate inversely proportional to 1/1 divided by the square root of the density, where pressure and temperature are kept constant, or rate of diffusion is inversely proportional to the square root of the relative molecular mass, where pressure and temperature are also kept constant. So R is the rate of diffusion, D is the density of the gas, and then M is the relative molecular mass. Okay, relative molecular mass. So we can use it to compare two gases with their rates at constant temperature and pressure. If the rate of diffusion of two gases are R1 and R2 under the same condition of temperature and pressure, their densities are D1 and D2, or their relative molecular mass are M1 and M2 respectively. So we can write the formula as follows. R1 over R2 equals to square root of D2 over square root of D1. Why do we need to do, say, D2 over square root of D2 over square root of D1? The reason is because there's an inverse proportionality, taking place. So it's the square root of D2 over D1, and then R1 over R2 equals to square root of M2 over square root of M1. M in this regard refers to the relative molecular mass. So the rate of diffusion is often calculated by measuring the time taken for a certain volume of gas to diffuse. Okay, to diffuse. Okay, so let's also take it a notch further and say that the rate of diffusion is often calculated by measuring the time taken for a certain volume of gas to diffuse. So rate of diffusion equals to volume over time. Volume over time. That's the rate of diffusion. So okay. So that's the rate of diffusion. So our R1 can be equals to V1 over T1. And then our R2 can be equals to V2 over T2. Substituting the above equation into R1, R2 equals to square root of M2 over square root of M1. What you end up having is that at equal volume, that is when V1 and if V1 equals to V2, that is our V1 over T1 multiplied by T2 over V2, V2 will be equals to square root of M2 over M1. Therefore, our T2 over T1 will be equals to square root of M2 over square root of M1. Okay. Having said that, let's look at this particular question and see how we can tackle, or we can use it to apply the Graham's law of diffusion formula. Okay, if 50 cm cube of oxygen diffuses through a porous plug in 10 seconds, how long will it take 100 cm cube of methane to diffuse through the same plug under similar conditions? Don't forget that our hydrogen has a relative atomic mass of 1, carbon 12, and oxygen to be 16. So applying Graham's law of diffusion, and what we are looking at is R1 over R2, which equals to square root of M2 over M1. So rate of diffusion of oxygen over rate of diffusion of methane equals to relative molecular mass of methane divided by the relative molecular mass of oxygen. So when you bring that in and you plug in the individual formulas, so what you will end up having is that you have the relative molecular mass. We try calculating it. Then the known entities that was given to us, we try to write them out. So our volume of oxygen is 50 cm cube. Our temperature is 10 seconds, and then our volume of methane to the 100 centigrade. Then the temperature is what we are looking for. We also know the relative molecular mass, and you can actually calculate that one easily. Okay. All right. So the next thing that is very important is to be able to establish a relationship between vapor density of gases and their relative molecular mass. We said that the relative molecular mass of a gas or vapor is the ratio between the mass of one molecule of the gas or vapor to to the mass of one atom of hydrogen. That's what the relative molecular mass is. Then vapor density, on the other hand, is the ratio of the mass of a certain volume of gas or vapor to the mass of an equal volume of hydrogen. So we said basically that vapor density is the ratio of the mass of a certain volume of a gas or vapor to the mass of an equal volume of hydrogen measured under the same temperature and pressure condition. So vapor density can thus be calculated using using the formula that says that vapor density equals to mass of given volume of a gas or vapor at STP divided by mass of the same volume of hydrogen. According to Avogadro's law, equal volumes of all gases contains an equal number of molecules. Thus, let the number of molecules in one volume because equals to n. Then, if that is the case, so if that is the case, what we'll have is that VD, as represented as standard temperature and pressure, is equal to mass of n molecules of the gas vapor at STP over the mass of n molecules of hydrogen. So canceling n, which is common, you get our vapor density to be mass of one molecule of a gas or vapor at STP over the mass of molecules of the hydrogen. However, since hydrogen is diatomic, so we have the vapor density to be equal to mass of one molecule of gas or vapor at so our vapor density is mass of one molecule of a gas at STP over mass of two atoms of hydrogen. So when you compare the formula of vapor density with relative molecular mass, they can be they can be what's it called represented as VD, which is vapor density as mass of one molecule of a gas or vapor at STP divided by 2 multiplied by mass of one atom of hydrogen. So relative molecular mass of hydrogen scale equals to mass of one molecule of gas mass of one molecule of gas of a gas or vapor at STP by mass of one atom of hydrogen. Okay, so the relation between vapor density of gases and their relative molecular mass. By substituting the relative molecular mass formula into the formula for VD, you have your vapor density to be relative molecular mass divided by 2. Now on cross. Now on cross multiplication, you have O2 times vapor density, which equals to relative molecular mass of a gas. So the relative molecular mass equals to 2 multiplied by vapor density, and that's the relationship. Relative molecular mass equals to 2 multiplied by what? The vapor density. So we've been able to look at kinetic theory of matter, try to explain the different states of matter and the phenomena that support kinetic theory of matter. We also looked at the gas laws, and then we have tried to, pardon me, please, we have tried to explain each of the gas law from Charles' law, Boyle's law, general gas law, and so on and so forth. And we used examples to buttress our point. Okay. So the evaluation questions are what I've stated here. But if you have questions based on this lesson, please don't hesitate to put them in the comment section and it will get to me. Please put your questions in the comment section and then I will respond to them accordingly. So these are the evaluation, these are the questions I've put together for evaluating this class. And the first question says that the kinetic theory of matter states that, so you look at the options and then You put what you feel is the right option in the comment section, and then I'll react to it accordingly. So, mm, so these are the evaluation questions. So you please go through them one after the other and ensure that you drop your answers in the comment section. I will pick them up and then I will do the needful to them, and then I will share with you. So please let's take note of all this lesson evaluation and ensure that you attempt them. Very, very important that you attempt. So that's that for that. So we have so many questions, so you can just look through them and then solve them, and then put your answer in the comment section. Thank you for listening, and I will see you for in the next video. Take care of yourself. Bye bye.